look at van der Waals equation. And what we did last time was that we saw that we could use canonical ensemble perturbation theory in powers of the attractive interaction between the long distance attractive interaction. So the short range interaction, which is repulsive, was taken into account by changing B to B minus B and excluded volume effect. And then the short range, the long range part, which we used, for which we used the 1/6 part of the Lennard-Jones potential. And that essentially gave rise to, in the pressure term, nkt over V minus B, that coming from over here. And then there was a constant times A minus V squared. There would be higher order terms, which would be like N4 over V, N cubed over V cubed, and so on and so forth. So, right, point is that what do the isotherms of this look like? And the point was that if I tried to plot the isotherms, then the PV diagram, I mean, it would look like your usual PV equal to constant, which is Boyle's law. I mean, if you ignore this B over here, then and the V square saying that essentially these terms are like, this is the density, this is equal to nkt, that's the number density. The next term is like n squared. And so if it is a really dilute gas, then you go with nkt, that n is n by n is equal to the number density n over. So, could you switch off your microphones? Crosstalk is not used, is problematic. So, it's nkt minus n squared and so on. So the initial part, I mean, when you are looking at this n over here at temperatures which are high enough, that is the dominant term, and you look more or less like the ideal gas PV equal to constant. And then what happens is that there is a critical temperature, and beyond which this develops. The PV curve becomes like this. As you can see, there is going to be a region, I mean, del P del V equal to 0 is a possibility. And so here are the points where del P del V equals 0. For this temperature, the roots of del P del V equal to 0 are all in the are all complex and or negative, and therefore you don't see any. But then there comes a particular temperature. This is the critical temperature where you see, this is where this P versus V curve, this point over here is where this del P del V is equal to 0, which means that if you were to look at this very closely, it is just slightly flat over there. So it is del P del V, I mean, that is just microscopically flat over here, del P del V equal to 0. That's the condition for this over here. And then it is more than that, because below this temperature, if you plot it up, it would look like this, which means that this maxima and this maximum and this minimum over here, they come and actually merge at this point over here. which means that at that particular point, it is not only del P del V which is 0, but the second derivative is also equal to 0. So this point is a point of inflection. It is, as you can see, that it is not a minimum, neither a maximum. The curve retains its sort of monotonic character over there, but just there, retains it. It is in this limiting situation where del P del V and the second derivative is equal to 0, making this a point of inflection. And as you go below that, temperatures T over here, which are less than Tc, and over here, this is T greater than Tc, separated by this curve over here, where it is T equal to Tc. This part is completely reasonable. This part over here, not reasonable, because this is telling you that between this point and this point over here, the pressure increases with volume. So that cannot be. And therefore, this is, so far as van der Waals equation goes, this is a sort of inadmissible region over here in some, that is, you can't, well, actually between this point and this point up to here, that is where the minimum is, it's all right. I mean, that is monotonic. Beyond the maximum, once again, monotonic. But in between over here, where the pressure increases with volume, that is not accessible region. What it means is that there is some kind of, there is a breakdown of this description over there. And this is essentially the coexisting region where you have a simultaneous gas and liquid phase in existence. It is the gas which is over here on this edge, and beyond you have the gas. On this edge and to the left you have the liquid phase, and in between you have a coexisting phase over here. So that curve over here, essentially the boundary is the coexistence curve, and in between is a coexisting region of liquid and gas, which van der Waals cannot handle. Beyond it, on the left or right, I mean, the liquid phase pressure change, you apply a lot of pressure to get a small change in volume. And on this side over here, back again to PV equal to constant. So, I mean, the pressure falls off as the volume extends. This is quite all right. This is quite all right. In the middle, the phase. All right. But what is important is that there has been a continuous transition over here. Right in the vicinity of this point, which is the critical isotherm, Tc, that is, this isotherm corresponds to T equal to Tc, separating this single phase region. Here it is all single phase. No matter how high the pressure, it still remains a gas. And now below Tc, you have a two-phase region. There is this coexisting region over here. So you pass continuously. So you are going continuously as you vary the temperature. As T is varied, you go from one phase region to two-phase region. So from one phase, it is just gas everywhere. And then down here, there is a coexisting phase of liquid gas with a liquid on this side, gas on this side. And that is happening without any question of any latent heat being given to the system, or the system giving out or absorbing any latent heat. It's a continuous transition. So the operative word is continuously, so no latent heat involved in this process. It is down here when you want to go from the gas phase to the liquid phase, there would be the question of supplying the latent heat or giving out the latent heat. So, but right here, the transition takes place continuously, and that unlike the first order transition that you go through over here from the gas phase to the liquid phase, over here you go from a single phase to a coexisting liquid gas phase continuously, and because of that, it is that continuity of this transition over here which gives rise to the very strong fluctuations. It's the strong fluctuations because the system does not really know whether it should be a gas or a liquid, and therefore there locally it is sort of like liquid over here, gas-like over here, and if you look at the container which has this liquid, you would try to look at it through light scattering, you would see it become very strongly turbid. So you can look up these light scattering pictures on the net, that somewhere where people are trying to scatter light exactly near this point over here from a system. The cleanest picture, something which could be done at room temperature, that instead of using a liquid gas system, it is more convenient to use a two liquid system, a liquid mixture, which has a similar behavior in the sense that the two mixtures are the two liquids are mixed homogeneously at high temperatures, and then at a certain critical temperature, they phase separate. When they are just in the vicinity of the phase separating temperature, there is this huge amount of fluctuation, and as you cool the system further, it becomes well separated. Meniscus develops in the liquid between the two phases. But just near and this is something which can be done at room temperature. You can choose the liquid mixture for this to happen at room temperature. And if you look up the net, a particular favorite is 3-methyl-pentane nitroethane. So this mixture has a critical point of 27 degrees centigrade, and therefore very good to work with. Actually, if one makes the right concentration mixture, one can demonstrate just by inventor trivially in class. That you can see that, but the thing.
Somebody's in the waiting room. Could you let him in?
So you can see these, as I said, you can quite spectacular. The mixture becoming turbid and looking completely non-transparent as you change the temperature ever so slightly. All right, so the point is, what we want to know is what is going on in this equation of state as I cross this temperature over here. So I want to know how does, for example, what does it mean to know what is going on? Well, the thing which you want to know is what is happening to the compressibility of the liquid. So the compressibility, that is, you want, what is happening means technically what is happening to the physical parameters of the liquid. What are the physical parameters? You want to know, for example, the elastic property, that is the bulk modulus of the liquid. You want to know the specific heat of the liquid. These are the, the bulk modulus actually gets related to the light scattering. So the fact that you can scatter light very easily, and look at it, the light scattering gets related to the susceptibility, the bulk modulus. So the physical quantities associated with this liquid over here would be, if I want to look at the static properties, responses, that is, I change the pressure a little bit on the liquid surface, how does the volume react to it? I give it a little heat, how does raise the temperature a little bit, how much heat does, add a little bit of heat, how much does the temperature change? So this kind, or I ask the dynamic question, that what happened to did something happen to the viscosity of the liquid? Did something happen to its thermal conductivity? So I can ask a whole set of questions. The questions are always about, practical questions are about what is called response functions. Response functions are the things by which you probe a system. You change a parameter which you can handle and then see how the conjugate parameter changes. So you change the pressure a bit, change pressure, and you want to see how does the volume respond. You heat it a bit, supply heat, and you want to know how does the temperature change. This is for equilibrium response functions. The other kind are the dynamic responses, which happens if you, with a gradient. So you have a velocity gradient. The thing which comes into account is the dynamic quantities that can come in. A velocity gradient produces the viscous response. Temperature gradient produces the thermal conductivity. So these are the fluids which are disturbed a little bit from equilibrium, and how does it come back to equilibrium. And what generally happens is that near this critical point, it takes it a long time to come back to equilibrium. So in particular with the thermal conductivity becomes extremely large, and it takes make a small temperature fluctuation, and for the system to come back to equilibrium takes a huge amount of time. The viscosity is somewhat better behaved, but still takes technically infinitely long relaxation time near at the critical point. So, all right, so it is the response functions, the static response functions, which are these, and the dynamic response functions, which are these. So you want to, we will not be doing dynamic responses in this class. We just wouldn't have the time, I think. But the static responses are more or less trivial to do, let's say, particularly in this case, the specific heat a little more difficult, but neither does the specific heat have a strong behavior, so nothing's lost. But for this susceptibility, it is very easy to get going. So, all right, so we want to explore now. I mean, this is the qualitative picture. Now we want to get down to actually try and get the numbers out of this, which in this case can be reasonably easy to do. So del P del V equal to 0. So critical Tc is determined by two conditions. It's a point of inflection. So I have to set del P del V equal to 0 and then also the next derivative equal to 0. So 0 equals, I have minus, let's take 1 mole of gas. So RT over V minus B squared plus 2A over V cubed. So that is for del P del V equal to 0. And then another derivative that is equal to 0. So it is 2RT divided by V minus B squared minus 6A over V cubed. And where is it 0? It is 0 at this point over here. The point is T equal to Tc, V equal to Vc, P equal to Pc. So that is the critical point. The only two independent variables really. So Tc and Vc, and the third follows from the equation of state. So critical point, it is a point determined, a point which is prescribed by prescribing the value of the critical temperature and the critical volume, or the critical temperature and the critical pressure. So if you were to do an experiment, you wouldn't be changing the volume of the liquid. What you would be handling is the pressure and the temperature. So whatever the critical, you put it over there and then scan the temperature. And so, all right. So that's now, so that means I go back and these over here, I have to put a C. Right? So then you divide, and there should have been a cube over here, and this should have been a 4. Sorry. So I was taking derivatives, first derivative, second derivative. So so I divide, and what do I get? So if I divide this by this, then it is Vc minus B divided by 2. And on this side over here, it is going to be, so I have Vc minus B go to the top there. So Vc goes to the top here, and 3 comes below. So 3Vc minus 3B is equal to 2Vc. So Vc is equal to 3B. So Vc is equal to 3B, and the R times Tc follows. R times Tc is equal to 2A times Vc minus B, which is 4B squared divided by Vc cubed over here, which is 27B cubed. So RTC equals where did I, this is 8. This is 2A Vc, should have been RTC is equal to 2A Vc minus B, that's 2B. 3b minus 2b, so 2b whole square. So that is 8 a over 27b. So RTC, the critical volume is 3b. The critical temperature is in RTC is 8a over 27b, and the critical pressure is to be can be found from this gas law. From here, RT over, so this is RTC divided by, so this is equal to RTC divided by 2B minus A divided by 9B squared. RTC is equal to 8A over 27B. So that makes this 4A over 27B squared. So 4A, 4 over 27, and this is 3 over 27. So it is A over 27B squared. So there you are. You have found. So now I can erase these. Let me, this condition I don't need. These I don't need. This is something I don't need either. Let me,
Sir,
yeah, we'll get rid of this. Yes, go ahead.
sir, could you please again tell why you use the conditions del P del V equal to 0 and del square P del V2 equal to 0?
Yeah. This isotherms, if you start plotting them up, they are going to be monotonic curves up to a certain point. You are looking at the function RT over V minus B divided by A over V squared. That's the function that you're looking at. If I plot up that function, then that function, if you are looking at very, if you are in a range where these B is very small and A is also very small, and therefore I can neglect this in some order, and you can imagine that if temperature is high enough, then all that will happen is that RT is going to dominate, and V is much greater than B. The graph is going to look like this. So isotherms are going to look like PV equal to constant. So that's what's going to happen over there. If I now make the temperature lower, then this term is going to become, these two terms are going to become competitive. If they are going to become competitive, then the first thing that will, and the pressure is not going to be negative, but competitive means that you can have a maximum or a minimum. So imagine that this term becoming very big over here, and eventually it has to decay. But if it becomes very big, then it is negative and becoming big, eating away at this term over here, which means that the chap, which if you look at the asymptote over here, which is like 1 over V, and now I add to it this 1 over V squared, that 1 over V squared is going to get subtracted from it. And so you are going to, this 1 over V chap is going to fall, and this fall over here eventually has to be mended. So it has to go through a maximum. And then again, I mean, if it is down here, I know the asymptote is like this, so it has to come and that. So if you look at the qualitative feature of this, either you plot it up or you try to understand the qualitative feature. It has to be a graph for low values of temperature, it has to be a graph which looks like this. High values of temperature, it has to be a graph which looks like this. So in between, as I change the temperature, the nature of it has to change. And what is meant by the nature of it changing, I will explore whether there is a derivative. What does the derivative of this function do? If I look at this, obviously it means that the derivative has to go to 0. The derivative has to go to 0 certainly at 2 points over here, and therefore otherwise, I mean, it will not eventually match up to this. And consequently, there has to be some point where these two are going to coalesce. If this coalesces with this, the second derivative has to vanish. So this point where the nature changes from this to this has to be a point of inflection.
Okay, sir.
So we are looking at this point of inflection over here, and I have this, and I got the critical temperatures as the critical point values, which are RTC equal to 8A over 27B. I have the critical volume, which is VC equal to 3B, and I have the critical pressure, which is this is RTC, which is 27B, and A over 27, somewhere along the line, PC is equal to, right here, it is A over PC, which is this, which is A over 27B squared. So A over 27B squared. So that's what I know. Now I want to know what is going on in the immediate vicinity of this. So I want to know what happens if T, or everything is uninteresting here, everything is uninteresting here. The only place which I'm interested in is this region over here, where T is equal to Tc into 1 plus epsilon. V is equal to Vc times, let's say, 1 plus delta. Haven't used it. So V is equal to Vc times 1 plus delta. T is equal to Tc times 1 plus. So I want epsilon, delta are all very small. So I'm interested only in the immediate vicinity. As I said, must have mentioned, immediate vicinity means that delta T over Tc is much, much smaller than 1. That is, this epsilon is like 10 to the power minus 2 or much smaller. So that's that's the only region where I'm interested. And the point is that, as luck would have it, that is really the only region where it is possible to do interesting calculations. If somebody wants me to find the susceptibility of the gas over here from a calculation, I would not be able to do it. Neither would I be able to calculate a pressure volume curve over here. But over here, unexpectedly, on the other hand, I mean, it's a dilute gas over here. It is some kind of a simpler problem in some sense over here, but certainly a very simple over here. But if somebody wants me to calculate the pressure very accurately in this point, I won't be able to do it, but over here I can. And the point is why, what exactly is meant by I can? So that is the interesting question. So T equal to, so I'm focusing on the immediate vicinity of this critical point. So this epsilon and delta are very small. So at the first thing I will calculate, I will be on the critical ISO code, which means set V equal to VC. So I'm going to sit, so here is this curve over here. I'm going to sit in this PV curve, here, it's V over here. I'm going to sit at this, my volume will be this VC over here. So the V is going to be kept at VC, and I'm going to change the temperature. So I'm going to change the temperature to, I'm going to write T equal to Tc times 1 plus epsilon, which I have already done. So that's the what I'm doing, that in the temperature axis, which you don't see, it's just that there is another isotherm over here, which looks like this. So I'm essentially going from this isotherm to the neighboring isotherm, which is epsilon away. And I want to check what happens if I want to calculate the response function. The thing which I'm going to calculate, what do I want to calculate? You only want to calculate things which can be measured. And what can be measured in a liquid? You can measure the compressibility. So chi of T equal to minus V del V del P at constant T. This is what it is called isothermal compressibility. So that's the, so it is like the susceptibility of a magnet. The susceptibility of the liquid is the compressibility, and you are interested in the isothermal compressibility. That is, the experiment will be done in a heat path, keeping the temperature constant, as opposed to doing a fast process in which the entropy remains a constant, which is an adiabatic process, and then it would be the adiabatic compressibility done with the entropy held fixed. So that's a far more difficult experiment, a far more difficult calculation, but fortunately, the spectacular thing is with the isothermal thing. So isothermal compressibility is this. And I want to look at isothermal compressibility for, as I said, Tc equal to 1 plus epsilon. So, all right, so what am I supposed to do? I'm supposed to have P equal to this, let me write, was RT over V minus B minus A over V squared. And where am I? I am at, so I want to calculate del P del V. So it is del P del V which I want to calculate. That's the inverse of this. And it is 2A over V squared minus RT over V minus B squared. And where do I want to calculate it? I want to calculate it at V equal to VC and T equal to this. So this is equal to 2A over VC. VC is your 3B. So that this is 9B squared minus, where am I? Temperature is RTC into 1 plus epsilon square, and V is at at the critical isochore, which is 3B. So this is my 4 times B square. So RTC, so here is 2A over 9B square minus RTC over 4B square, but RTC is 8A over 27B. So this is equal to, so this is equal to 2A over 9B squared minus RTC, which is 8A over 27B del P del V. This should have been a cubed. Where, which one? Here. This is a cube, this is a square. So my 2A over V cubed minus RT over V minus B squared. So it is 2B divided by this, which is 27B cubed minus RTC over V minus B squared, TC into 1 plus epsilon squared, and then it is 2B, which is 4B squared. So this is equal to 2A over 27B cubed minus RTC, which is 8A over 27B. So this is 2A over 27B cubed into 1 plus epsilon. So this is so chi of T is equal to, so this is minus 1 over VC, which is 3B, and then it is 1 over this. So now what? The 1 has cancelled this term over here, and this answer is minus 2A over 27B cubed times epsilon. So it is plus, and you go 27B cubed over here divided by 2A into epsilon, which is 9B squared over. So here you are. The susceptibility, isothermal susceptibility chi of T is equal to a constant which depends on the gas. B changes from gas to gas, A changes from gas to gas. So there is some chi 0 which changes from gas to gas divided by epsilon, which is universal. Epsilon is T minus Tc over Tc and is the same thing for every gas. Tc can change, but epsilon is something that you fix according to this definition of it over here. And in terms of that, what you find is that chi of T is going to diverge as 1 over epsilon, no matter what the gas is that you have taken to do the experiment with. It doesn't matter whether you are looking at carbon dioxide or nitrogen or oxygen or whatever it can be, but it is always 1 over epsilon. That is a behavior in the immediate vicinity. Mind you, there can be, I mean, this calculation over here is for the van der Waals gas is fortuitous. It gives us as an exact answer. That is rubbish. I mean, if I had taken a different equation of state, I would find that this is not an exact answer. But the primary feature would be that for small epsilon, this would always be the answer. The calculation from any equation of state which you, if I do it from a given equation of state which does not look at local fluctuations, you simply look at the question of existence of the critical point. There are, I mean, at the enough problems going on inside the liquid so that it goes from a gas phase to a single phase to a two-phase region. But it is a sort of overall view. You are not looking at it with, I mean, actually the local fluctuations that are going on. But this is, I mean, what these things are called are mean field theories, that you are given a good description of pressure as a function of volume and temperature. You take it, you find where there is a critical point, you do a calculation, and you find that the isothermal susceptibility is going to blow up as 1 over epsilon as the system comes. So it is a huge response. This, you change the pressure ever so slightly and the volume changes a huge amount. This is because the system does not know whether it wants to be a liquid or whether it wants to be a gas. It is going into, when you are in this little bit of region over here, you sort of don't know whether it's a gas phase which is favored or a liquid phase which is favored. You sort of swish back and forth between the two, and it is this not knowing what to do which gives this huge response over here. A very small change in the pressure can take you from the liquid density to a gas density or vice versa, and an infinitesimal change can produce a huge amount of change in the volume. So small change in pressure, large change in volume. The net result is that the susceptibility becomes very small. The isothermal susceptibility, mind you, the adiabatic susceptibility behaves very differently. It is the isothermal susceptibility which is spectacular, and it goes as 1 over T minus Tc. So chi of T goes as 1. So it is singular. So at T equal to Tc, the chi is no longer an analytic function of temperature. It blows up. It's a singular function. And it is not that it is a pole or anything. It is just fortuitous that you got an epsilon over here. The real answer is that it should have gone, the calculation should have given you chi of T is proportional to 1 minus T, 1 to the power T minus Tc to the power 1.26 something. Sorry, 246. So that's what if you do the experiments, that is what you find. It certainly, I mean, blows up as T goes near Tc, and the exponent with which it blows up is 1.246 and so on, not the one which I have found over here. And the discrepancy is because I started out with an equation of state which has a lot of averaging done over it, over the local behavior. I'm not paying attention to the local fluctuations in the gas. I'm doing what you will learn is called a mean field theory. You ignore fluctuations at certain level and you look at mean quantities, and that leads to, generally leads to physical answers. Certainly in D equal to 3, it gives you very often the right physics. but miss us out on this. Now, what do I mean by gives you the right physics in D? If this tells over here, I have not used the spatial dimension at all. So this answer which you have, that chi of t goes like 1.246, the experimental result is true only for d equal to 3. If I did a d equal to 2 and you don't have a liquid gas transition, but you can do a magnetic transition over there, and the magnet is no different from the fluid, as we will see if it is a uniaxial magnet. But then the answer is very different. This over here is dimension independent. This answer tells you that regardless, so long as this is your equation of state, whether it is spatial dimension 1, 2, 3, 4, what have you, the answer is that susceptibility diverges with the exponent 1.246. It's not bad in d equal to 3. As I said, if you do the experiment in d equal to 3, you get 1, and 1 and 1.25 are not that far apart. But things just go bad. If you go to d equal to 1, you would have no transition, and there would be no question of finding something like this at a finite TC. There is no finite TC in d equal to 1. It's all at t equal to 0. And then in d equal to 2, the Ising model, which is the analog of this, the one component Ising model, has exponent which is 1.75, which is now very far away from 1. So the point is that in d equal to 3, you are not doing too badly. So you have to understand that there are, this kind of an approach, the positives and negative. It is a trivial, it gives you the answer trivially. You have got a completely non-trivial answer by doing a few steps on the blackboard. That is great. But you also have to realize that that answer would have to be hemmed in by many other constraints. You have to figure out when is it good and when is it bad, and so on and so forth. So those things would have to be, so it may not always be the right answer, but it can show you the way to the right answer. The important thing about this answer is that it is a universal quantity. It is 1.21, it is epsilon to the power 1, regardless of what gas you are using and what the critical temperature is, which depends obviously on the gas. So there is a hidden universe, there is a universality in it. It is not to say that all gases have the same value of chi of t, chi sub t. That's not true. The chi 0 differs from gas to gas. Nobody calculates that, or I'll put it more bluntly, nobody can calculate that. But what you can calculate is the fact that it diverges and there is an exponent, and that exponent is actually universal and is independent of what material you are using. So the pluses and minuses. It gives you the first glance into universality, that there will be a divergence of the susceptibility over here. That divergence is going to be of the same kind regardless of the material. And that's the positive part. And the negative part is that it says that dimension of space plays no role. That is not correct. And that is the most important issue about the failure. And the fact that it is not absolutely right is another. So but you have set the ball rolling, you have an answer, you now can build on. But then let's look at something else. There is a this is a trivial calculation, but then there is a more non-trivial calculation giving you something which is equally strong. So we want to now look at what happens below the critical point. And
Sir,
yeah,
one student is in the waiting room. He got disconnected.
there's nobody in the waiting room right now. Yeah. So the next thing is a little more complicated. I want to go below the critical point and so here is T fixed. So that is some T which is equal to Tc1 minus epsilon. So I go slightly below the critical point. And I picture myself in this mixing zone, where there is this coexistence part. Over here, it's all liquid. Here, it's all gas. This part, which is the unphysical part of the van der Waals equation, below Tc, below T equal to Tc, this unphysical part is because of the is because of this coexistence. So all right, if I want to look at this isotherm and I want to calculate the density at this limiting point and density at this limiting point. So this corresponds to some V1, let's say. This corresponds, so this turning point is at V1, this turning point is at V2, so it is V1 and V2, which would be found from the extrema of this curve over here. And I want to know what is this, the density difference between, I want to know the delta rho, which is the density difference between liquid and gas very near T equal to Tc. So that is what I want to know. What is the density difference as between the liquid and gas? So T is going to be set at Tc times 1 minus epsilon, epsilon much smaller than 1. So I'm going to look at delta rho, which will come out as delta V actually. I'm going to take a fixed mass of gas and I'm going to calculate V1 and V2. So delta rho would emerge as V1 minus V2 divided by V squared. So your temperature is slightly, and the V1 and the V2 would be obtained from V equal to, by writing V equal to Vc, which is the critical point, this point Vc, times 1, let's say, plus delta. And delta again is very small. So temperature is fixed below, and V is going to be some Vc times something, and that something is what I want to find given that epsilon is fixed. And so once again, I need to go back to my starting point and all along I'm going to sit at the critical, the pressure is, keep the pressure fixed at the critical pressure, and I'm varying the, I'm sitting at temperature slightly below and looking at it. So I'm going to go back to this question of I'm interested in finding these 2 points over here. So P, which is equal to RT over V minus B minus A over V square. I'm interested in finding the points where del P del V has this change. So del P del V equal to 0. So that is a 0, which is equal to minus RT over V minus B square plus 2A over V cubed. So del P del V equal to 0. These are the two. I want to find the coordinates, these 2 points at which your del P del V is equal to 0. So I want to essentially solve this equation and find these 2 points over here. So I'm going to solve it given that T is equal to, so I'm looking at RT C into 1 minus epsilon divided by V minus B square is equal to 2 over V cubed. So that is what I have to do. T equal, and what is V? V is equal to Vc into 1 plus delta. So this is equal to 2A over Vc cubed, and then it is 1 plus delta to the power minus 3. And on this side over here, it is RTC into 1 minus epsilon divided by Vc, which is your V is equal to Vc into 1 plus what did I get? Delta. So Vc into 1 plus delta minus B whole square, that is equal to 2A over Vc cube into 1 plus delta to the power minus 3. Vc is 3B. So this chap over here is 3B minus B, which is 2B, and then it is plus 3B times delta. So RTC, so this side becomes RTC into 1 minus epsilon divided by, it is 2B plus 3B. So I take out 2B over here. So it is 4B square, and then it is 1 plus 3 delta by 2 square. That is equal to 2A over Vc cube. So it is 2A over 27B cube into 1 plus delta to the power minus 3. So please, I mean, this there is a cancellation which has to occur, and so please keep watch the. I mean, keep. I can make an algebra. If I make an algebraic error, it's all gone. So please, I mean, be very watchful of what is going on. So RTC over 4b squared. So RTC is 8a. 8a by 27b, and then I have 1 by 4b squared, and I have 1 minus epsilon 1 plus 3 delta by 2 whole square, and this is equal to 2a over 27b cubed into 1 plus delta to the minus 3. So 2a over 27b cubed. So that this is 4 cancelling this. So it is 2a and 27b cubed. So this cancels with this over here. So this cancels, that cancels, and now I have 1 minus epsilon. So 1 minus epsilon is equal to 1 plus 3 delta whole square. So it is 1 plus 9 by 4 delta square plus 3 delta, right? Into this has to be expanded. It is 1 minus 3 delta, and then the next term is going to be, so it is 1 minus 1 plus n times x plus n into n minus 1 by 2. So that is minus 3 minus 4 by 2, that should be 6. So plus 6 delta square and so on. So yeah, right. So this is equal to 1, and now the linear terms plus 3 delta, so that cancels out with the minus 3 delta. So I have 1, and this gives 9 over 4 delta square. And then this with the 1 gives me 6 delta square, and this the delta and the delta gives me 9 delta square. So that is up to then. Next term is delta cube, which I'll stop at the first. So it is minus 3. So it is minus 3 and plus 9 by 4. So it is minus 12 by 4. So this is equal to minus 3 by 4 delta square. So you see what has happened. And 1 minus epsilon is 1 minus 3 by 4 delta square. So delta is equal to 2 by root 3 plus minus epsilon to the power half. So that is telling you that, look, here is my VC somewhere sitting over here, and there is one root which is slightly higher than VC. So V1 is equal to VC into 1 plus 2 by root 3 epsilon to the power half. And the other, which is V2, is equal to VC minus 1 by 2 root 3, 1 minus 2 root 3 epsilon to the power half. My interest was in delta rho, and delta rho is m over v. So start out with a given mass of gas, and this rho is equal to m over v 1 minus m over V2. So that is the density difference delta rho, which is equal to, the two V's are nearly equal. So this is roughly m times delta V divided by, so all this is near V critical. So it is this delta V over VC. So the delta V over VC is this. So this delta rho is equal to m divided by VC times the 4 by root 3 epsilon to the power half. So that is the next striking answer. Delta rho proportional to epsilon to the power half. You see, that is again non-trivial. Every liquid which is undergoing this transition, critical point transition, the second order phase transition near the critical point of the liquid, the transition second order meaning no latent heat is involved. You have this coexisting phases, and the coexisting phases have a density difference which is proportional to epsilon to the power half. So at this point, at the critical point, which is this Tc over here, it is just one point, which is delta rho is equal to 0, and then it starts splitting, and the splitting goes the liquid phase and the gas phase coexisting with each other with a density difference which increases as you go lower and lower in temperature. So absolutely striking result that this half is independent of what liquid you have, what liquid you are considering, and that it's universal. It's a universal exponent. Does not matter what liquid you are doing the experiment with. If this is what you measure as a function of this number will always be half. So just as with the susceptibility, the number is always 1, the number, this exponent is always was always 1 there, is always half over here. The prefactors are non-universal, but the exponents are universal, and therefore, once again, this van der Waals equation having this feature is something which is very striking. So you see the critical point in van der Waals equation, you see the universality emerging, that it is an epsilon to the power half and epsilon to the power minus 1 for these two quantities without any question. And how, once again, it's all a question of, it works in d equal to 3. Does not work in d equal to 2, 1 or 4, 5. So there would get it all, you can get it all messed up. But it is delta rho, which is epsilon to the power half. Not so bad in d equal to 4, 5 and so on, really. I mean, if you do simulations, those are, but 2 and 1, yeah, you can be, 1 is impossible, 2 is going to be bad. So so d equal to 3, where it is more sort of meaningful, is that the answer is actually 1/3, very close to 1/3. So instead of 1/3, you have got a half. So not all that bad. It is a start, and why is it so? So d equal to 3 works. And why is d equal to 2 or d equal to 1 so bad? It's a question of fluctuations. Fluctuations become very big in d equal to 2, even bigger in d. So lower the dimensionality of space, higher the fluctuations are, and so life is bad. if you go to higher dimensions, actually fluctuations are small, and eventually you would, if you could go to infinitely many dimensions, you would be seeing things which look in some sense. All right. But low dimensions, you go below, if we stick to what is physical, then d equal to 2, d equal to 1, the fluctuations are much bigger, and therefore the answers are worse. I mean, the fluctuations are so strong in d equal to 1 that they don't let you order, and in d equal to 2, it is just marginal, but yeah, that's so. All right, so you have these two very striking answers coming out of the more or less trivial manipulations, and therefore this is a good thing to have. So we recognize that what is good, which is that you can do it. We also recognize that the answer is not the most accurate, and therefore things are there can be there is a lot of scope for improvement. So all right, so much for van der Waals gas, that you see for the first time that there is a transition, which is a transition without any latent heat. So you have a second order phase transition. No latent heat is involved in it, and you see that the response function diverges. So chi, the isothermal thing, goes as T minus Tc to the power minus half, and the coexistence curve has the behavior where delta rho is proportional to Tc minus T. This is minus 1, and this is the power half. What if I went through a calculation of the specific heat for the van der Waals gas? If I looked at CV for the van der Waals gas, when there is no critical behavior. So the phenomenology, so there is going to be some number, these exponents would have to be given some kind of nomenclature, and the nomenclature is that the isothermal susceptibility diverges near the critical point with an exponent gamma. The coexistence curve, delta rho, is proportional to T minus Tc to the power beta. The specific heat at constant volume is proportional to T minus Tc to the power minus alpha. So there is a delta, which is that you sit at T equal to Tc, and ask how the delta rho changes. So at if I easier to put it in terms of the magnetic language, that if so this has an immediate carryover to the magnetic system, that Tc could have been the Curie point, you look at the magnetization as a function of T. So the spontaneous magnetization as a function of temperature. High temperature, there is no magnetization. And then at some critical temperature, the magnetization comes and starts getting bigger. So here is the picture for the magnetic phase transition. Then the chi temperature would be del M del H. That's at constant T. The delta rho equivalent would be M proportional to, that is the spontaneous magnetization. For T less than Tc. So M not equal to 0 for T less than Tc. And at Tc, if I switch on a little bit of, so this is del M del H at some T, and then you come and sit at T equal to Tc. At T equal to Tc, your magnetization is proportional to H to the power 1 over delta. So, so if I, if in the limit of H tending to 0, I don't have any magnetization at T equal to Tc. It is only when you go below T equal to Tc that the magnetization shows up. And this del M del H has to do with the fluctuating part above Tc and also the below Tc, but there is a question below Tc of a spontaneous magnetization and that, if I look at the H, if I put in an external field H, then the magnetization at T equal to Tc would not be equal to 0, but would be proportional to 1 over delta, H to the power 1 over delta. So let's put the spontaneous magnetization as something like MC. So it is at the critical point, and then M is the average value which you see below Tc. So at T equal to exactly at Tc, MC is equal to 0. It grows only below Tc, and that is governed by so if I put on field H then and sit at Tc, the magnetization is going to grow as the field grows, and it is going to grow with an exponent which is 1 over delta. So that defines the exponent delta over here. The corresponding language, it would be that this delta rho over here, you sit at T equal to Tc, and you would have to vary the delta rho proportional to P minus Pc to the power 1 over delta if T is equal to Tc. So you change the pressure from the around the critical pressure, and you can get some density produced at, if you sit at T equal to Tc, just as all these are with this sitting at P equal to Pc. But now, I mean, if I sit at T equal to Tc and let it change pressure from its critical value, there would still be a delta rho. And like the quantity over here, it would be 1 over delta. All these exponents, alpha, beta, gamma, delta, are universal in the sense that they depend on, for example, this over here, it's independent of the fluid. If I talk about a magnet, then life is a little more complicated. The question is, what kind of a magnet? Is the magnetization over here? That is not an important issue. The rho, which is the density, is a scalar. It can and can only be a scalar. Over here, it is the magnetization, and that need not be a scalar. If it is a question of uniaxial magnets, or the Ising kind of magnet, where spins only point up or down. So spins pointing up or down, which is the Ising magnet, in that case over here, M is completely analogous to delta rho. So the M and delta rho are analogous if it is a Ising model for magnets. So Ising spins only point up or point down. So density is only the delta rho can only be plus or minus. That is, it is either greater than the critical dense rho c or smaller than the rho c. So there are two possible values of delta rho sitting on that coexistence curve that we drew a few minutes ago. The two extremes of the coexisting, the 1 and 2, which we talked about, points were V1 and V2. So there is that delta rho, and that delta rho is completely analogous. But this analogy breaks down if I talk about magnet. It is no longer spin up or spin down. The spin is actually a vector. So the magnetic system is far richer, that the magnetization can actually be a vector, and then the Ising model becomes a Heisenberg model. So taking the M from, and now life is far more difficult. That is the two-component M is different from the three-component M, and so on and so forth. So whether the magnetization vector can point in any direction in space, that is the when the magnetization vector is a three-dimensional vector, but if it can only orient in a plane, then the magnetization can be a two-dimensional vector. And you can see I now have in that magnet picture, you have two vectors to talk about. There is the spatial behavior. Space is has a dimension 1, 2, or 3, line, plane, and 3D space. The magnetization can also have you can have a one-dimensional line on which, so here is a one-dimensional line on which the magnets are sitting at various sites, and the Ising magnet can only point up or point down. That is the Ising case, which is like the liquid gas. But sitting at that point, it can be that the magnet can rotate in the magnetization can rotate perpendicular to the board. So it can rotate in that plane over there, and then it is a two-dimensional magnet. The magnetic vector can rotate, but then the tip of it can possibly rotate in the third direction, and then you have a three-dimensional magnet. So the one-dimensional line can have a one-dimensional magnet, two-dimensional magnet, or three-dimensional magnet. So these two entities, D, which is the dimensionality of space, and N, which is the dimensionality of, this is the space dimension, this is the magnetization dimension. They are completely independent of each other. So when one talks about these exponents over here, what happens is that if a transition, phase transition does occur, then these exponents are functions only of N and B. So that is what is universality really, that one has to understand universal does not mean that everything is the same. No, but if the D and N are both same, then the critical behavior is going to be the same. So that's one thing which you have to keep in mind. And all right, so that's that. We have covered more or less what the phenomenology goes. All right, so we have reached a point where one can talk about a magnetic system next, and it is a system which you have seen already, and which is the Ising model. So we will talk about the Ising system next, and then within the Ising system, see what is the analog of this calculation over here. That is the mean field theory, which we just carried out for the gas, which meant I started out with equation of state which ignored a lot of fluctuations. It was an equation of state between average values. So the average values recognize that there is some probability distribution, but that you have fluctuations around the average values was essentially ignored. And we will take up the Ising model in the next class. You are familiar with the D equal to 1, so I don't have to, the point is, all right, there are things I want to do with, we'll see. I mean, but D equal to 1 is what we need to start out with. Certain points in D equal to 1 are interesting and capable of. So just for completeness, you are familiar with the D equal to 1. We'll quickly go over the D equal to 1 and then look at the mean field theory. The D equal to 1 has the advantage that it can be done exactly. So but mean field is what right now the analogy is with the mean field. So we need to worry about what's a mean field with D equal to 1 and exactly how does that go over to D equal to 2 or D equal to 3. So that's for the next group of things. So all right. So here we are. I mean, a reasonable point to stop.